Hi and welcome to the series of lessons where we will see some real implementation of stateful processing. And we will start by aggregations. So after my previous explanations, you may be thinking that the aggregation is a kind of aggregated results or aggregated representation of the state of the input events. And you may be thinking it's cool because it's so memory efficient and I will be able to write them and use in small machines. But in fact, it depends again. It depends on the type of aggregations you want to have. If you have a sample count, sample sum, well, that's fine. You probably don't need a lot of memory to buffer the results. On the other hand, if you need to have something much more exact, precise, like for example the distinct count, distinct sum, well, you will need kind of a much bigger buffer to store as well the value, so sum count, and also the records that you already seen. And that's the reason why I divided these aggregation lessons into two parts. So the first one is called the reducible aggregations. And here the idea is that you can combine different results without storing necessarily the whole state, like for example doing the sum. So when you do the sum, you simply need the sum for the previous period, and you simply addition it with new data, and same logic for the count. So here is the example. We have our window, which is t minus 1, and we have input data with window, which is t. And when you combine both, you get a new value to the state, and you can also emit a new value to your downstream consumers. So it's memory efficient. There are different examples, but it's not always the single values you will need to store. For example, if you need an average, we'll obviously need two values. And maybe I think that for the percentiles, it will be even harder to have something concise, like for min or max aggregations. And yes, here's the example for the average, where you can see that we don't store the aggregation result in the state store, but rather than that, we store only the values that are used to generate it. And depending on the logic, you might be storing more or less data than these only two attributes. The second kind of aggregation is the cumulative aggregations. So the aggregations that require much more records in the state store that simply a few values. And here, as I said before, the idea is to have everything that concerns the uniqueness. Generally, you will need to store much more data. For example, if you need count distinct, when you need to store things you saw before, and also combine them with the new things you have in the input. Same if you want to store only the unique input, so to drop duplicates. And there is also something the other when you try to compute the skewness. Well, you need also store the values for the previous data and put them in balance with the new data to get the skew distribution. So let's take an example for the count distinct. We have different items in the memory, we have different items in the input, and you can see that we got our items IDs separate because we don't store the duplicated number 1 for the first window and the and yes, that's currently the single duplicate. And as you can see, it's less memory efficient than the previous aggregation method, but it's more flexible. You can cover more use cases with that. And there is also another part when you can write aggregates either for groups. So for example, you want to count or sum something for a user, you will obviously group by user plus your aggregation, or you can simply aggregate or you can simply write full aggregates and emit the results continuously. And that's all for this lesson. So aggregations, remember these two different phases when you can reduce the state and, well, probably not worry too much about hardware pressure, memory pressure, and the other case that requires much more data in the state store, and in that case you will probably need to monitor this memory for the state store or fine-tune it much better. Thanks for watching and see you in the next lesson.